Hi everyone, so today we will be learning about Gibbs free energy and chemical equilibrium. So before you start this video, um, before we proceed, please make sure that you watch the previous video, which is the second law of thermodynamics. It's a prerequisite lesson for understanding Gibbs free energy. So we know that in predicting the spontaneity of a process, the enthalpy factor is considered in conjunction with entropy factor. So this means that when we solve for in determining for the spontaneity of a process, if it's spontaneous or not, if we recall from the second law of thermodynamics, we used the enthalpy factor as well as the entropy factor. So the balance between these two quantities is given by another state of function called the free energy or Gibbs free energy. So please don't be bored by this long text. I'll try to sum it all up. So the balance between these two quantities is given by another state function called the Gibbs free energy. So when we balance the factors for enthalpy and entropy, we have this Gibbs free energy. It's represented by G as it is named after the proponent William Gibbs. So for a reaction to take place at a constant temperature and pressure, so note that this is constant. Not in a standard conditions. The sign of the free energy change at standard conditions. On the other hand, indicates whether a reaction will attain a state of equilibrium or run to completion. So if we are given standard temperature and pressure, the sign of the Gibbs free energy change at standard conditions. And this will let us know if the answer or the value tells us to for the reaction to run into completion or if it's in chemical equilibrium. So I can elaborate this in a few minutes. So before that, let us know that free energy represented by G is a portion of energy change in spontaneous reaction that is available to do useful work. So the maximum amount of work that can be done by the system on its surroundings at constant temperature and pressure. So these points are very important. Gibbs free energy is the maximum amount of work that can be done by the system on its surroundings at constant temperature and pressure. So we talked about Gibbs free energy in a spontaneous process. Now let's go ahead. What is Gibbs free energy in non-spontaneous process? So it is the free energy. The free energy is a measure of minimum amount of work. So it's in a spontaneous process. In spontaneous, it is the maximum amount. It's the maximum amount of work. But in non-spontaneous process, it is the minimum amount of work that must be done on the system in order to drive off the reaction. So take note of this difference. So in non-spontaneous, it is the minimum amount of work. So in this equation, if we look at this equation here, G refers to the G, H, S are all refer to the system. Okay, these are all referring to the system, not the surroundings and not on the universe. So it's just on the system. So H and S are um, enthalpy and entropy. And the triangle here let us know that it's the change, okay? It's a change in constant temperature. We have constant values. So it is the change of the system. Gibbs free here is a change of the system. So note that this equation is valid in all conditions. If both temperature and pressure are constant, so you know that here in a constant, we can say that constant conditions, the values are given for temperature and pressure. However, at standard conditions, it's fixed that the temperature is 25 degrees Celsius and the pressure is at 1 atmospheric pressure. So if you recall this in our previous lessons, okay, note the difference between constant and standard conditions. So note that this equation is valid in all conditions. If both temperature and pressure are constant, the relationship between the sign of the delta G and the spontaneity of a reaction is as follows. So note that if the change in G is negative or is less than 0, the reaction is spontaneous in the forward direction. If it is greater than 0 or it's positive, it is non-spontaneous in the forward direction. So work must be supplied to make it occur, or an energy is required for the process to continue, or for the conversion to work. And finally, if the change in Gibbs free energy is equal to 0, the reaction is at equilibrium. When we say equilibrium, it's from the word equality or equal. The states are all neutral. Okay? So let's go ahead and solve for a sample problem. So we have this example here. So it says, calculate the standard change of Gibbs free energy from the standard enthalpy of formation and standard entropy values, and predict whether the following reaction is spontaneous or not at 25 degrees Celsius. So we have this chemical equation here. So we have this given for H2, the enthalpy, change of enthalpy is 0. If you're from my STEM class, if you're the one to first comment why this is 0, then I'll give you plus points, okay? So if you're watching this, feel free to comment down. We'll definitely give you a plus points in your quizzes. So tell me why this one is 0. So the entropy change is for H2 is 130.6 and so on. So these are the values, okay? And the next one would be the solution, okay? So we are asked to find the standard change of free energy. So the solution would be, we should approach this one in a step-by-step basis. Note that to solve for G, we need the change in enthalpy in standard condition minus the temperature times the change in entropy. Okay, so the temperature here should be in Kelvin. So for this whole reaction, we will first need the standard change in enthalpy, followed by the standard change of entropy. So let us first solve for enthalpy change at in standard conditions. So we know that the formula for this is summation of y hf products. Please do watch the previous videos so you can easily catch up. So we have, for the product side, we have H2O and CO. So this is already a balanced equation. So we have 1 mole. Let's first start with H2O. 1 mole of H2O times the its standard enthalpy change, negative 241.8. Negative 241.8 kilojoule per mole, plus the second component in the product, we have CO. We have also 1 mole of that. 1 mole of CO times its standard enthalpy change of formation, we have negative 110.5 kilojoule per mole. So square bracket. So we are done with the product side. Let's proceed to the reactant side. So I'm just going to put the minus sign here. And for the reactant side, we have 2 components as well. We have H2 and CO2 gases. So for H2, we have 1 mole of H2, and its standard enthalpy of formation is 0, plus 1 mole of CO2. So CO2 is negative 393.5 kilojoule per mole. So let me use another color to cancel the units out. So we have to cancel this one and this one since it's multiplied by 0. Okay. So if you use your calculator, please correct me if I'm wrong. So this one is negative 352.3 kilojoule plus it's minus negative 393.5 kilojoule. So we have should be, so this is negative 352.3 kilojoule plus 393.5 kilojoule. Sometimes I get wrong answers. So this one is 41.2 kilojoule. So this is our standard enthalpy change for the reaction. So this is the step 1. So just going to so the second component we will be looking for is the standard entropy change. So let's look for it. This is the second step. You have the formula for this. If you check out the entropy video, you'll know how to solve this by now. So that's the formula. And then again we have 1 mole of H2O, and its entropy change entropy is entropy at standard condition is 188.8. It's 188.8 joule per mole, okay, plus 1 mole of the second component. The second component is CO, and we have 197.9 entropy at standard conditions. So this is 197.9 joule mole Kelvin. So let's close this bracket. And then we subtract the second component. We have the reactant side. So for the reactant side, we have 1 mole of H2 and 130.6. We have 1 mole of H2 plus times 130.6 joule per mole Kelvin, plus the second component in the reactant side, we have 1 mole of CO2, and then if we go back, we have 213.6 joule per mole to Kelvin. And let's close this up. So this is the formula. And then we use our calculators to solve. We have joule per Kelvin na, minus 344.2 joule per Kelvin. Since we're canceling out the common units, so we then have 0.0425 kilojoule per Kelvin. No. We first have 42.5 joule per Kelvin, but we want this to be kilojoule per Kelvin, so we multiply this by 1 kilojoule is equivalent to 1000 joules. So we cancel this one, and then we'll have 0.0425 kilojoule per Kelvin. That's how you solve for the standard entropy change. Now finally, we completed our components. We have this one. We have the enthalpy change at standard conditions and temperature times the entropy change in standard conditions. So our enthalpy is 41.2 kilojoule plus the temperature at standard conditions is 25 degrees Celsius. In Kelvin, that is 200. No. This is minus. (298) Kelvin times 0.0425 kilojoule per Kelvin. So we cancel common terms. So the answer for this would be, if you can solve this, let me use my calculator. Have 41.2 minus, it's 298 times 0.0425. We have 12.67. So 41.2 to minus 12.67, we will have 28.53 kilojoule. And from our previous discussion on the concept, if we have a Gibbs free change greater than 0, this is non-spontaneous, okay, in the forward direction. So work must be supplied. There should be an energy required. There should be work to be supplied in order for this reaction to happen. So in your answers, I want to see that you indicate that this is non-spontaneous. And energy, let's just use the term work. Work is required for the reaction to happen. So this is a second example. This is found in your activity. So if you made it this far in this video, you'll surely perfect the quiz for this lesson. So this is actually in your letter A in your activity. So this carbon here is a graphite. It's a solid. So in this problem, we have an easier approach since the standard change of enthalpy and entropy are given. But in the previous example, only the standard enthalpy change of formation and standard entropy is given. So it's not like this one. So it's just the entropy at standard condition. But here it's spoon-fed. We already have this given. It's what we need, right? So the approach for this is much more straightforward. So the solution for this one is, so we have to solve for the standard entropy of the reaction. We have it's actually given here in joules per Kelvin. So note that it's joules per Kelvin. It's already given, but the unit is joules per Kelvin. And we want this to be kilojoules. So what we do here is simply to convert this one. We have 183.6 joule per Kelvin times 1 kilojoule over 1000 joules. So we cancel common units, and then we will have 0.1863 kilojoule per Kelvin. And then finally, let's solve for the Gibbs free energy change. Have this formula. So we have negative 749 kilojoule minus 298 Kelvin times 0.1863 kilojoule per Kelvin. So we will have the final answer in kilojoules. So it's negative 129.52. Please double check kilojoules. So this is a negative value. So it's a spontaneous reaction. It happens without work required. So by solving this first in first item, you'll be able to solve the following items B and C in your activity. So I hope you learned something in this video. So thank you for watching.